Hello and welcome to this GCSE Chemistry video about electrolysis. This is part 2 of electrolysis, and in this video we'll focus on why and how we use electrolysis for metal extraction, and then we'll focus in particular on the extraction of aluminium from aluminium oxide. Humans use metals for a huge variety of things, from building materials to vehicles, from pipes to wiring. We get these metals from the Earth's crust, but we don't find them just as the pure metal normally inside the crust. They're normally in types of rock referred to as ores. Now, the ore is a rock that contains some metal compounds within them, and these compounds are things that are normally ionic compounds where there is a metal bonded ionically to some non-metals, so with iron and oxygen, copper and sulfur combined together to make these metal compounds that contains the metal that we want. Traditionally, to get these metals out, we first of all need to create a mine. Now, a mine involves digging the rock from under the ground and then moving the rock to somewhere where it will be processed and then disposing of a large amount of rock once we have finished. Having separated the metal compound from the rest of the rock, we need to separate the metal itself from the non-metal that it is bonded with. Let's give an example of iron bonded to oxygen. To do this, we have a variety of options depending on what the metal is. You learn more about this in another topic, but typically this will involve something called smelting, where something more reactive than that metal takes away the oxygen, for instance, and this process of removing oxygen from the ionic compound is referred to as reduction, and the chemical that is taking the oxygen away from the compound is called the reducing agent. And the reducing agent, in this case carbon was the example, it must be more reactive than the metal that the oxygen is being taken away from. Otherwise, the reducing agent won't be reactive enough to take the oxygen away. We won't be able to use smelting to separate the metal from the metal compound. And in this case, when we have metals that are highly reactive, high up that reactivity series, we have to use electrolysis. Electrolysis is the name for the process where we use electrical energy, or we might say we use an electric current, to make a chemical reaction happen. In the case of metal extraction, the reaction that takes place is the splitting apart of an ionic compound from the metal ore. And in that process, we provide the energy by using an electric current. And we start with a metal compound, and you can tell it's an ionic compound because there is a positive particle and a negative particle. These are the two ions, a positive ion and a negative ion. And the electrical energy provides the driving force to separate these ions. Remember, they are held together by strong electrostatic forces of attraction in the 3D lattice when the ionic compound is a solid. And these electrostatic attractions are strong and they require a lot of energy to overcome, and that energy comes from the electric current. After the process has been carried out, we end up with the metal in its element form with no charge, and the non-metal element also with no charge. We say that the ions have been discharged because they have lost the charge that they had before when they were in the ionic compound. Electrolysis needs to be used for metal extraction if the metal is more reactive than carbon. This means that the metal that we're trying to extract is too reactive to be separated by reduction by the carbon, and the carbon is not reactive enough to take the oxygen away. We also use electrolysis to extract a metal if the metal might react with carbon during the smelting process. This would lead to the formation of metal carbides or possibly other undesirable side reactions. When we carry out electrolysis, the ions in the ionic compound need to be able to move. And so this means that we can't use a solid because the ions in the solid can only vibrate slightly about a fixed position. And so this means that we need to melt the ionic compound to produce a liquid. And we call this liquid the electrolyte. And since it has ions that are free to move, it can conduct electricity. And so when the power supply is turned on, the cell or the battery will provide the electrical energy that's needed to make the electrodes become positively and negatively charged. And we call the positive electrode the anode and the negative electrode the cathode. These will typically be made out of some inert material. That means it's unreactive. And most commonly we use graphite, which is a form of carbon, and that does have delocalized electrons which will conduct electricity. And these delocalized electrons move through the electrodes and through the wires. Once we've got our positive and negative electrodes, the ions will be free to move through the liquid, and this enables them to be separated because they are attracted to and move towards their oppositely charged electrodes. And when they get there, they become discharged. This process requires a large amount of energy because in order to extract the metal, we need to first melt the ionic compound, and we need a lot of energy to produce the electrical current needed for electrolysis. You need to know about the use of electrolysis to extract aluminium from its ore. Aluminium is extracted from an ore called bauxite, which is a mixture that contains aluminium oxide, typically between 15 to 25% aluminium in that mixture. And we can tell that it's a mixture rather than a compound due to this variable percentage within the ore. The extraction process takes place in something called an electrolysis cell, which is a gigantic steel container that is lined with carbon. And this carbon is actually the negative electrode for the process, the cathode. And then dipped into our electrolyte is the positive electrodes, and these are called the anode, and these are also made from carbon. And the electrolyte itself is our aluminium oxide. And aluminium oxide has got the chemical formula Al2O3, and we could work this out because aluminium is in group 3 with 3 electrons in its outer shell, which means when it loses those 3 electrons, it becomes a 3+ ion. It transfers those electrons to the non-metal oxygen. And oxygen is in group 6, and so it gains 2 electrons to become a 2- ion. And so these ions combine together in a ratio of 2 aluminium to 3 oxide. Aluminium oxide has got a very high melting point. And so the electrolyte is actually a mixture of molten aluminium oxide and cryolite. Cryolite is another ionic compound that contains aluminium, and here is its formula. Now you'll notice that it contains sodium, but this doesn't actually interfere with the electrolysis process because sodium is more reactive than aluminium. And we do this because the mixture has a lower melting point than pure aluminium oxide. And this means that we can use a lower operating temperature, which allows us to use less energy, and so therefore use fewer energy resources. For instance, burning less coal to generate that energy, and this will also save money and mean that there will be larger profits. The electrolysis of aluminium oxide all takes place inside this electrolysis cell that I'm showing here. And so we've got our steel case, our layer of carbon, and then we've got our mixture of molten aluminium oxide and cryolite. Dipped into this electrolyte, we've got some further pieces of carbon, which will become the other electrode, and then we've got some electrical circuitry here. To begin the process, we turn on the power supply, and that creates an electric current because electrons will flow from this electrode to this electrode. And we can represent the positive and negative terminals of the power supply just by simple notation, as I'm showing here and here. But it's delocalized electrons that move through the circuitry, and they build up on this electrode, which makes it negatively charged. The aluminium ions are positively charged, and so they are attracted to and move towards the negative electrode. When they get to the negative electrode, they will gain electrons and they will be discharged, meaning that they will lose their charge. And then molten aluminium will collect at the bottom of the cell, where periodically it could be pumped out, or they could open some kind of connection here and allow it to run out from this container into a separate container. Meanwhile, those oxide ions, they are negatively charged, and so they will be attracted to the positive electrode, and so they'll move towards that. When they get there, those negative oxide ions will become discharged, and then they will form the element oxygen, which has got the formula O2. And so oxygen gas will be formed as a result of this process. And so overall, what we've done is we've separated our aluminium ions from our oxide ions, and we've ended up with the two elements, aluminium and oxygen. In the process of electrolyzing the aluminium oxide, the oxide ions are attracted to the positive electrode, where they become discharged and form the element oxygen. Now, since this is all taking place at a high temperature in order to melt the aluminium oxide to allow the electric current to flow, then actually a further chemical reaction takes place at the positive electrode that results in the positive electrode needing to be replaced periodically, sometimes as frequently as once per month. This could in fact be the subject of an extended response exam question worth as many as 4 marks, and the question might ask you to explain why the positive electrode, or why the anode, needs to be replaced. And to get those 4 marks, you need to say each of these things. Firstly, the positive electrode is made of carbon. That gets us 1 mark. And at this positive electrode, we are producing the gas oxygen. And then for the 3rd mark, we need to say, well, this electrode will react with the oxygen, or we could say that it gets oxidized, and as a result of that, we produce carbon dioxide gas. And this would give all the appearance of that positive electrode literally burning away because it's all taking place at such a high temperature. Instead of writing that as a sentence, to get marking point number 3 and number 4, you could instead write a chemical equation for the process that is occurring. And that equation would have carbon, which has come from the electrode, reacting with oxygen that formed at the electrode, and turning into carbon dioxide gas. Or you could even write that as a symbol equation with C for carbon, reacting with the oxygen that was forming and turning into carbon dioxide gas. And as a result of that, the electrode would be almost literally burning away during the process. The overall reaction taking place during the electrolysis of anything is always a redox reaction. And that's a reaction where one substance undergoes reduction and another undergoes oxidation. And we can use the acronym oil rig to help us remember what those two phrases are. Firstly, oxidation is loss, and that means of electrons, and reduction is gain of electrons. And so something is oxidized and something is reduced. Now, in the electrolysis of aluminium oxide, the aluminium ions collect at the negative electrode where they lose their charge. And so we can write what's called a reduction half equation for this process. And so the ion loses its charge. We need to remember that. And so we start with aluminium 3+, and it turns into aluminium without any charge, and that would just be Al. And so we can tell that the positive charge of this aluminium ion is getting reduced. And that means it must be gaining electrons in order to go from 3 plus to 0. And so we write electrons on the left-hand side of this half equation. And instead of just gaining 1 electron, aluminium actually needs to gain 3 electrons to go from +3 to +2 to +1 to 0. That needs to be balanced. It was already balanced in terms of the aluminium atoms, but it needed to be balanced in terms of charge. We had +3 from the aluminium. We need to have 3 single 1 minuses from the electrons in order for those positives and negatives to cancel out. And so the aluminium has been reduced because it is gaining electrons. Meanwhile, at the positive electrode, the oxide ions are losing electrons, and so the oxide ions must be getting oxidized. And that would make sense if you think about the fact that if the aluminium was being reduced at one electrode, at the opposite electrode, the oxide must be being oxidized. Different processes happen at the different electrodes. At the negative electrode, reduction always occurs. At the positive electrode, oxidation always occurs. And we can write a half equation for this oxidation, for the oxide ion becoming discharged. To do this, we start by putting the negative oxide ion, and it's losing its charge, so it's going to become oxygen without any charge. Now, oxygen is a diatomic element. That means that it doesn't go around as separate O atoms, it goes around as O2. And so now this half equation looks quite a bit more complicated than the aluminium half equation, because we've got 2 oxygen atoms on the right hand side, but only 1 on the left. And so we need to balance this in the conventional way of balancing, which means that we need to put a 2 in front of the oxide ion. And so that means that we in fact need to have 2 oxide ions being oxidized at the same time. And then in terms of electrons, in terms of charge, we have got 2 oxide ions. So that means we've got 2 lots of -2 on the left-hand side. And so the total negative charge here is -4. Whereas on the right-hand side, we've got this neutral oxygen molecule, which doesn't have any charge. Its charge is 0. And so we need to add electrons to this half equation to make them -4 on both sides. And since electrons have a negative charge, they need to go on the right-hand side. And since the left-hand side was -4, we need to add 4 -1 charge electrons in order for that to balance. And so now the right-hand side is 4- and the left-hand side is 4-. So this half equation is balanced. If you prefer, you can write the half equation for oxidation with a minus sign in front of 4 electrons, but have the electrons on the left. If it makes more sense to you that the electrons are shown as being minus when they're being lost, then you can write it like this. Both of these 2 half equations would be fine in an exam situation. I have a preference for the first one, but they're both fine. Okay, that's the end of this video. Thanks for listening.